All right, so here are the problems that we're going to do for chapter 26. These are the only problems that we're going to do from the chapter review. All right, so number 1, number 2, number 3, 4, and 8. All right, so let's take a look at those. All right, so here's number 1. And number 1 and number 2 are related to each other, by the way. All right, so number 1 says, what's the greatest distance at which a galaxy survey sensitive to objects as faint as 20th magnitude could detect a galaxy as bright as the Milky Way, which has an absolute magnitude of -20. All right, and let me read the second one too, because we're gonna just continue with that one. Assume the standard Hubble constant H0 equals 70 kilometers per second per megaparsec. Estimate the redshift of the Milky Way at that distance calculated in the previous problem. All right, so we need to answer that first. All right, so let's switch to this, and all right. All right, so here we're going to do the problem. All right, so I've already set this up. Hold on, let me make sure something. All right, so I've written out the numbers. So it's the apparent magnitude is +20, the absolute magnitude is -20. So we use our standard equation to find distances. The distance is 10 to the power of the absolute magnitude. I'm sorry, the apparent magnitude minus the absolute magnitude plus 5 divided by 5. All right, so we put all those numbers in there. So it's 20, minus a -20, which makes it 40 plus 5, 45 divided by 5 is 9. All right, so it just comes out to be 10 to the 9th parsecs, and we want that to actually be in megaparsecs, and the reason is because of the second problem here. So in the second problem, it says, okay, use that distance and Hubble's constant to come up with what the redshift is. All right, so what we have to do is we have to figure out what the recession velocity is. And remember, the recession velocity, as chapter 26 points out quite correctly, is the recession velocity is it has nothing to do with the actual motion of an individual galaxy. It's rather the effect of the expansion of space itself, the expansion of the universe itself. All right. So anyhow, so this recession velocity. Let's see. Where's my mouse? Oh, there it is. So the recession velocity is equal to the Hubble constant, 70 kilometers per second per megaparsec times, in this case, 10,000 megaparsecs, right? I'm sorry, 1,000 megaparsecs. And so the megaparsecs, see, this is why we had to have it in megaparsecs. The megaparsecs cancel, and that leaves us with 70 times 1,000, or 70,000 kilometers per second. All right, so then what we do is we have to figure out what the redshift is. So once we know that it's 70,000, all right, let me get this set up for the next one. So once we know the recession velocity is 70,000, that's the only thing that's really important for this, to get the redshift. So 70,000 kilometers per second. It's supposed to be a K, kilometers per second. All right, and the other thing that we need to know, of course, is what's the speed of light in kilometers per second. That's, of course, 3 times 10 to the 5th, right? If it's in kilometers per second, it's 3 times 10 to the 5th kilometers per second. All right, and so the redshift, what we call the redshift is is equal to the velocity of something divided by the speed of light. And since the velocity is in kilometers per second, and we have to have the speed of light in kilometers per second, which of course we do already, so it's 70,000 divided by 3 times 10 to the fifth. And both of them, of course, are in kilometers per second. Kilometers per second, which cancel. So anyhow, 70 divided by 3 times 10 to the fifth gives us a redshift of 0.23. All right. So that's it. And it's, the redshift is just a pure number. All right, let's go on to problem number 3. Actually, let's just take a look at problem number 3 while we're thinking about it. So problem number 3 says, if the entire universe were filled with Milky Way-like galaxies, so a galaxy approximately the same mass as the Milky Way, and that's not a bad approximation, with an average density of 0.1 galaxies per cubic megaparsec. All right, so that's a strange sense of density, okay, but that's, so you think of 0.1 or 1/10 the mass of the Milky Way per megaparsec, right, instead of per cubic megaparsec, instead of like a cubic meter, which we normally would think of as, kilograms per cubic meter. So this is going to be, Milky Way galaxies per cubic megaparsec, which, remember, that's a huge volume of space. A million parsecs, like imagine a cube, a million parsecs by a million parsecs by a million parsecs. Anyhow, calculate the total number of galaxies observed by the survey in problem 1. All right, so again, we're the thing about problem 1 is you're looking at 1,000 1,000 megaparsecs. That's the key to that. All right, so for this particular problem, we have from problem number 1, we have a radius. So let's look at this circle right here. We have a radius of 1,000 megaparsecs. So the formula for the volume is 4 pi divided by 3 times the radius, whatever it happens to be. Sometimes it's in meters, sometimes it's in kilometers. In this case, it's in megaparsecs. But we have to cube that. All right, so here's the formula over here. So 4 pi divided by 3 times 1,000 megaparsecs cubed gives us a number of 4.189. We probably could have rounded that to 4.2 times 10 to the 9th megaparsecs cubed. All right, so the key to doing this is they give us the density. The density, the average density is, this has to do with the universe itself, is about 0.1 galaxies per cubic megaparsec. So remember, that comes from, I think it was, what was it, five hydrogen atoms per cubic meter, or something like that, and so you kind of extrapolate that out. It's approximately how much mass per cubic megaparsec would exist. Anyhow, to figure out the number of galaxies, all right, we know what the volume. Remember, what density is the density is the mass. In this case, it's going to be the number of galaxies, right? So this is going to be the number of galaxies. Galaxy, and let's just pretend that's galaxy, per volume. All right, and we just calculated what the volume is, right? So there's the volume. This is what the density is, and so we're going to put those two things together and solve for the number of galaxies. So basically, we just multiply V times 0.1, and actually, you can probably already see what the answer is. V, the megaparsecs cubed or cubic megaparsecs will cancel, and so this, instead of being here, let me just let me get some more room here so that we can see what I'm doing here. All right, so the number of galaxies. All right, so I'm just solving this for the number of galaxies. The number of galaxies with a density of 0.1 times the mass of the Milky Way. And essentially, we're just going to do it in terms of masses of the Milky Way. So it's going to be 0.1 galaxies, Milky Way galaxies really, per megaparsec cubed. Right, so this is our cubic megaparsec times. Remember that number. I'm going to round it to 4.2, so it's going to be 4.2 times 10 to the ninth. 10 to the ninth, and of course that's remember that's the volume that we got, megaparsecs cubed. And notice the megaparsecs cubed in the denominator cancels the megaparsecs cubed in the numerator. And so really all that happens when you multiply by 0.1, the number of galaxies turn out to be 4.2 times, instead of times 10 to the ninth, it's now times 10 to the eighth galaxies, right? Galaxies the size of the Milky Way. Galaxies. All right, that's supposed to be an X. Anyhow, so that is number 3. All right, let's see, what's the next one? All right, I think the next one's number 4. All right, let's take a quick look at that. Number 4 says, according to the Big Bang theory, described in this chapter, without a cosmological constant. Okay, so remember that's now thought, we're not using it, but just to remind ourselves what that is, that was Einstein's famous blunder, but has now found new life in the fact that the universe is expanding, is accelerating its expansion. But we're not going to consider that. So they want to know what's the maximum age given these different Hubble constants. All right, we're going to use the modern one, 70. We're also going to use 60 and 80 because just a few years ago there was a lot of uncertainty in these. All right, so let's see, make sure